I admit I don't do it. Every day I plan, I'll do it, but day goes by and I don't know. I don't even leave my table.
You're tied down to work so much, but nevertheless.
चलो 70 होगी, अब क्या दिक्कत है यार?
दिक्कत नहीं साहब, ऐसा नहीं.
Done and dusted, finished.
Mm-hmm. Vic, how is Pauline and how is June? June must be studying in a big class now and growing into a very beautiful girl.
Lady. Oh, yes. Yes. That's my granddaughter. Yes.
Yes.
So we have another granddaughter, Aspen.
Okay.
And, she's also very big, but she's June is Ted's daughter, and then Aspen is Trent's daughter.
Okay, Trent's daughter. Okay, very nice. Yeah. And you have moved to Oregon, or you're still in Tucson?
We live we half the year in Oregon, but not this year because of COVID. Yeah, we're in Tucson, but we go up to Oregon in summer.
Okay.
Yeah.
Okay. I will come and visit you sometimes very soon.
Okay. Well.
Hey, I think we are live on YouTube, so we can start. On behalf of the President, Association of Quaternary Researchers, Dr. Vanna Prasad, Vice President Dr. Pradeep Srivastava, and all the members of AOQR, I welcome Professor Victor R. Baker. I welcome all my seniors here, all my colleagues and friends linked today on this virtual platform to listen to the second talk of the bi-monthly web talk series to be given by a legend, Professor Victor R. Baker. He's Regents Professor of Hydrology and Atmospheric Sciences, Geoscience and Planetary Sciences, University of Arizona. In the US, the title Regents Professor serves as a recognition of the highest academic level and is awarded to faculty members who have made a unique contribution to the quality of the university through distinguished accomplishments in teaching, research, and creative work. As you know, that the key objective of the association is to bring the Indian quaternary research at par with the global research developments in terms of latest techniques, methods, and practices, and enable to fill in the gaps in the available data set. In line with this objective, the association seeks to organize regular meetings, conferences, field workshops, laboratory training sessions, brainstorming sessions, and open panel discussions. In these times of the increased virtual meetings and seminars and decreased in-person events due to the global pandemic, the association saw the need to adapt and organize a virtual webinar series and talks. Last year, we did the ECR webinar series entitled Emerging Areas of Research in Quaternary Science to provide early career researchers a platform to share their work to a global network of interested individuals and students. This year, 2021, we designed this bi-monthly web talk series, Legends Talk, and bring on this platform and hear and interact with the legends of quaternary science. And today is the second talk of the series. We know Professor Victor Baker very well, but I still want to introduce him and say a few words about him and his work, and it's my proud privilege to do so. Professor Victor R. Baker is PhD in geology from University of Colorado in 1971. After working as a hydrologist and a geophysicist for the U.S. Geological Survey in New York and Colorado, he was on the faculty of the University of Texas at Austin. In 1981, he moved to the Department of Geosciences, University of Arizona, first as a full professor, and then in 1988 as one of the first University of Arizona's Regents Professor. From 1996 to 2004, he was at the department. He was the department head of the Department of Hydrology and Water Resources, which is now Hydrology and Atmospheric Sciences, University of Arizona. Professor Baker's researchers have dealt with the key issues in paleo flood hydrology, a field he defined in the 1970s and 80s, and flood geomorphology, channels, valleys, and geomorphic features on the Mars and Venus, catastrophic Pleistocene mega flooding in the northwestern US and Central Asia, history and philosophy of the earth and planetary science, and the intersection of environmental science with public policy. Professor Baker has authored and co-authored more than 1,100 scientific contributions, including 20 books, 443 research articles and chapters, more than 550 abstracts and research reports, 34 extended technical reports, 42 encyclopedia articles, 39 published book reviews, plus guidebook contribution, and various other writings, including popular works in science. It's an honor for us that Professor Baker is here, and I thank him for having so humbly accepting this invitation to deliver a talk in the AOQR platform. With these few words about this great personality of quaternary science, I again welcome Professor R. Baker and invite him to deliver his talk, Discovering Possible Future in the Past, in reference to quaternary paleofloods and the prevention of natural disasters. Over to you, Professor Baker. You can share your screen.
So, Vinitaji.
Okay, thank you very much for this wonderful introduction.
Sorry, Vic. Yeah, may I ask everybody to mute their mics because there is an echo. Hema, please.
Yeah.
Everybody.
Okay, so I feel very honored to be here and to be back in India. It's only virtual, I know, but I spent many happy times here in the field with Vishwas and Hema and others. So I'll press the Present Now button and go to the screen. Let's see. Screen to share. Select window. Entire screen. Okay. Allow screen. So can you is my screen visible now?
Yeah.
Okay. So I will start the talk.
No, it's
Okay.
Professor Baker, your screen is not yet visible. You have to do present now. It's still not present. Yes,
Yeah,
now it's coming.
Now it's coming. Just
Yeah,
No, it's there. It's there.
Now it's visible. Okay.
Not visible.
Yeah, now.
It's visible. Okay, so I will begin the talk. So we are going to talk about this subject utilizing the theme of flooding. And on the left is real flooding with real people who are experiencing the event. On the right is how a lot of science of flooding is presented. For those whom this is not familiar, this is a flood frequency curve. And on the y-axis is the discharge magnitude of the flooding. And on the x-axis is a measure of probability, a conceptual concept that has to do with risk and uncertainty. And there is a very rare event that is used as a standard. This comes from engineering, which is the 1% probability that a flood that large could be equaled or exceeded in any year. The inverse of that is 100 years, and so this is called a 100-year flood. Now, my emphasis here is going to be on geology and particularly quaternary geology. But I'm not talking about geology as a bunch of facts about the Earth, even though the science gets viewed that way. I'm going to talk about geology as thinking. Broadly construed, geology, and I will pose this as a hypothesis, is intellectually the most important science for all humankind, more important than any other. And there have been a lot of philosophers and others, including many scientists, who have almost universally been on an intellectual track that really misunderstands the nature of science and the relationship of science to human welfare. Now, the way to get back on this track is to make more use of geological thinking. And I'll have to try to, in a short time, show how this fits in regard to the problem of flooding. But this issue involves communication of science to the public, to politicians, to leaders. It involves science education, and it involves how this works, particularly in a democracy, and also the future habitability of our planet, which is at risk from phenomena like flooding. So the big problem is reducing flood impact on people. And part of the answer is dealing with this problem of not communicating about flooding. A symptom of the problem is this idea that gets exemplified by the 100-year flood concept that I showed at the beginning. This is used by many hydrologists, many engineers, and it is almost totally misunderstood by those who have to cope with flood hazards, including political leaders, decision makers, and most of the general public. It also defies common sense because it's not the real time that people experience. It's the inverse of an annual exceedance probability. And its only relationship is that it has units really of fake time, not real time. The other issue is that in dealing with this, all of the talk by the technical people has been in terms of probabilities, when what we really should be talking about is possibilities. And probability itself is not understood by the public and certainly not by politicians. So there's a general infatuation in the public and political world with the concept of predicting the future. I think it is the responsibility of science to emphasize most emphatically that science does not make prophecy. It cannot say what the future is because that is totally impossible. Science works because it provides reliable guidance. It doesn't provide absolute certainty. There is absolute certainty, but that can only be provided by nature. And nature does not make fake news. Nature does not tell lies, and nature does not make mistakes. It is up to quaternary scientists to reliably tell us what Earth is saying about hazardous processes. And it is the responsibility of the quaternary scientists to be aid in communicating Earth's message. So we all know that climate change is enhancing extremes of temperature, extremes of drought, extremes of flooding. So how should we prepare for this? We are really being bombarded with official policies where engineers calculate flood probabilities in terms of uncertainties, and normal people, and as I said, most of the politicians do not understand this at all. The alternative is to listen to nature, to look for the natural signs of flooding, and to take advantage of the certainty that what has happened can happen. This is to talk about real possibilities. So my experience goes back more than 50 years. And you can say that what I do is I listen to floods themselves. And to do this, I formulated back in the 1980s, actually the work was being done in the 70s, a whole field of science called Paleo flood hydrology, which is the study of past or ancient floods occurring before our direct scientific measurement and observation. And this paleo flood hydrology looks for natural signs or evidence of past floods. For example, in a typical flood channel, there may be effects on vegetation, effects on sediments, and effects of producing a special kind of deposit called the slackwater deposit. Now, when really big floods happen, nature screams at us, there was an incredible big flood. This is a boulder that was transported about 16,000 years ago in the largest freshwater floods that we know occurred on planet Earth. So this is the area I did my PhD work in the late 1960s. It's the northwestern United States, and it's where a giant ice sheet came out of Canada, and it blocked the river drainages and produced an immensely deep, 800-meter deep glacial lake. And when that lake failed at the ice dam, it generated these catastrophic features: huge gravel bars, eroded bedrock, giant fluvial dunes, and the giant boulders that you saw in the previous picture. So my work on that topic, which is very academic, has spread around the world. Here is the pattern of catastrophic flooding in the northwestern U.S., where this glacier came down into the state of Washington, northern Idaho, and Montana. And the yellow shows the pattern of catastrophic flooding that ultimately went out to the Pacific Ocean. Initially, 50, 60 years ago, this was thought to be unique. But what we have found is that this pattern of flooding occurred all over the Earth at the height of the last ice age, when there were giant ice sheets covering parts of the continents, particularly northern hemisphere, because that's where the largest ice sheets and continental masses were. So shown on the lower left is North America. All these numbers refer to catastrophic flooding evidence associated with the last ice age. And the pink shows the distribution of sedimentation that was produced by these catastrophic floods. Over on the other side, you can see upside down is North America. The glacial lakes are shown in purple, and the glaciers are shown in the light blue. But at the bottom, you can see Asia and Europe. And we have numerous examples of what are now called mega flooding that occurred during the last ice age. Now, of course, this is all very academic. We don't have these giant glaciers today. We have much smaller floods, but it is the extremes of those floods that are posing the greatest hazard. And so what I started to do in the 1970s was to study the kinds of floods, still very extreme, that can occur and pose a potential hazard for today. So this picture shows flooding in Texas from a tropical cyclone in 1978. And on the left, you see the sediment-charged water. And on the right, you see after the floodwater dropped, there is a sand deposit, a slackwater deposit. And these slackwater deposits can be studied stratigraphically in the field to provide evidence of multiple flooding. The important thing about them is that they are nature's record of the most extreme floods. And those most extreme floods are the things that scientifically we know the least about because they are rare. But nature is very good at preserving the evidence of those extreme floods. So here is from studies that I was doing in India, beginning in the late 80s and into the 1990s. We did a lot of work together with Vishwas Kali and Sheila Mishra, who's in the picture here, on the Narmada River. And this is one of the stratigraphic sites that was worked up there. And you see a 2,000-year record of the flooding, along with the various individual flood layers and other evidence of the environmental changes that were occurring at the time of that flooding. Now, I can't go into a lot of detail about exactly how we analyze these results, but we utilize new computer programs for hydraulic analysis, and we can take those frequency kinds of plots that the engineers do, shown in blue, and we can extend them with paleoflood data that we generate that's highly quantified and very accurate for the extreme events that occur. So this is in line with the conventional way of thinking about those floods. Notice the 100-year flood is here. The conventional record only goes up to a relatively short time period, and all of these red dots are the paleo floods that carry us out to an understanding of the characteristics of the extremes that nature presents. In essence, we are interpreting nature's habits. We can also compare this to other quaternary records, and you all know of quaternary records on various kinds of phenomena. They often manifest themselves as wiggly lines, and here we have the whole Holocene back about 10,000 years with different paleo records, and then a kind of probabilistic analysis of paleo flood data showing the peaks in the data. This is for the general southwestern United States. We can also look at patterns of paleo flood in regard to the Earth's climate system. So here you see a kind of generalized map. At the top, you see in the yellow paleo flood sites in different parts of the world, including India, and you see the source areas and general patterns of tropical cyclones, which are capable of generating the largest floods on certain size drainage basins. On the bottom, you can see the 500 millibar atmospheric circulation pattern that alternates between the northern hemisphere summer and the southern hemisphere summer, intertropical convergence zone indicated by the dashed line. And of course, this is the pattern that is associated with the South Asian monsoon. So I want to get back to this issue of communicating the flood hazard and the risk. And I want to talk about the general problem that the extremes seem to be becoming worse problems in terms of damage, in terms of potential loss of life. We're worried about tropical storms getting more intense, that they may be more frequent. We are having increasing costs from damages, and we're dealing with phenomena that are the least understood scientifically. One approach that has been argued by those critical of the conventional statistical analysis is called the black swan theory. It basically points out that we are seeing phenomena that are a surprise. And this isn't just in nature. This is seen in the financial world, where the models that predict are not working, especially for extremes. They don't predict the most catastrophic thing is that some geologists, they were quaternary geologists at Tohoku University in Sendai, Japan. They were paleontologists, and they studied the Sendai Plain, which you see here being inundated. And here is a test pit in the Sendai Plain, and you can see the white is the shells that tsunami waves have emplaced across the plain. And in black is the carbon-rich soil that developed on that surface. It can be radiocarbon dated, of course, and you have 3 tsunami events. And they found that 1,000 years ago, a tsunami wave as big as the one that happened in 2011 had happened there. Nature spoke. They actually published and gave this to Tokyo Power and Electric, who did not act upon it. They used the physical analysis that I showed you as being more authoritative. Fukushima was a human-caused disaster. Unaware or suppressing nature's actualities, viewing them as unknowns, they used an impressive appearing but assumption-based physical reasoning to predict an outcome that was totally wrong and resulted in the most disastrous loss of money, certainly, so far in Earth history. And this is not a unique event. So this is my point. We learn from nature, not from the assumptions we make to do very elegant-looking physical analyses. Reasoning in science requires assessing, making discoveries about the phenomenon of interest. The phenomenon of interest here is rare great flooding. And we should not get beyond the limitations of our presumptions. We should not dismiss something like what nature can generate, because if we dismiss possibilities, we learn nothing about them, and that is a certainty. A truly scientific approach to extreme flooding requires attention to a reverse kind of scaling, where we extrapolate downward from potentially hazardous but geologically important floods, using what evidence can be obtained for the most extreme kinds of flooding phenomena found in nature. So nature is ultimately our teacher, and we have to be humble about this. Predictive models that rely on deductive reasoning, they explicate what is already known. They use existing facts. That's not science. Science is discovering new things, and nature is filled with opportunities for discovery. The most important goal of science is to generate new understanding. And there are logic problems with the conventional way that science is being done. This is the name of one of those logic problems called underdetermination of theory by data. I don't have time to discuss that, but I will continue with examples of what nature is doing for us. So to advance understanding of extreme floods, we need to have information on that real kind of flooding. And models won't solve this for us. We need the evidence for what has happened. So although it seems less elegant scientifically, what nature says to us, and the word for this is abductive inference, as opposed to what scientists say about nature, the deductive and inductive approach, that has better prospects in regard to conveying wisdom to our current society, including political leaders. So flood hazards are best understood in what has actually happened. And they are the sorts of things that actually can happen. They are not abstractions conveyed by experts who make law-based mathematical predictions of what should happen, but only if all the many commonly unstated assumptions are absolutely correct. And that is the problem. Now, there was a place that I visited in Japan that had no loss of life and almost trivial damage. It was a place called Onyoshi, and that had the highest surge height of any town, 40 meters high. But the people there in the 19th century had their town destroyed by a tsunami. And they put up markers, and this is one of them, on the hillside at the level of that wave. And that marker says, don't build below this point or your homes will be destroyed. And they rebuilt their town above the level of the tsunami. So this was a sign to them made by other people. But nature itself provides those signs. And this is what we do with an abductive kind of science. We look at evidence, indicators, signs, traces of the phenomena of interest. And here we're talking about flooding, but we could be talking about drought. We could be talking about extreme temperature. We could be talking about all kinds of issues. And we discover things. The experienced investigator, not a theorist or modeler, then infers the conditions or causes by which these phenomena could be produced. And we look at the relationships of those causes to effects that are tested in terms of consistency, coherence, and consilience with related phenomena. And there's a logic that is associated with this. Again, I don't have time to discuss it, that is called causal overdetermination. It has to do with the abundance of evidence, particularly on extremes, that nature leaves for us. So back to the theme of communicating hazard and risk as quaternary geologists. We need to do more to change the message from costs to values. Not just money, but what is the right thing? What is the good thing to do? We need to replace probability talk with possibility talk. We need to communicate what nature says instead of what experts say, relying upon their assumptions. And we need to use abductive or an investigative approach to interpret what nature is saying. So with one exception, the only certainty about future happenings is that what we can know about them is absolutely uncertain. That one exception is the real possibility that what has happened can happen. And that's maybe the last thing I want to leave you with. And I hope you're all still here. And I will, I guess, be open to discussion if I can move back to that part of the program. Do I have to press anything, or can you hear me?
Yeah, thank you.
Yeah.
Thank you. Mr. Baker, you can just press on the
Okay, so I will stop presentation. Let's see here. Okay. Okay,
Yeah.
I see you. I guess you see me.
Yes,
If you don't have questions, you maybe have been asleep or something. 'Cause this should give questions.
Interesting. Down here. Hello.
Yes.
Rajesh, you want to say something? I could see you raise your hand. Just see that you.
Yeah, a small question.
Okay.
Sir, it was very nice and very philosophical talk for me. I have just a small query regarding this. When geologists make this hazard assessment of a particular place, you know, whether it's a paleo tsunami or paleo flood. So they restrict most of the time what I feel to the area which has been damaged earlier, and somehow the anthropogenic climate change, the present day climate warming is creating new centers also. I mean, what I mean, if something has happened at particular one place in one city, the next hazard may not come at the same location. It may be, locally different. How to do this kind of assessment on a spatial scale?
Yes, this is an important question, and it has to do with how we can use what nature presents to us to help with not predicting the future, but understanding future possibilities. And that is not going to be going exactly from what happened at one particular place. But we know that in the Quaternary, that the patterns of climate and interaction with the land surface have shifted. So the kinds of storms that affect one place moved to a different place.
Yes.
And that will happen in the future.
Yes.
So what the past is telling us about is how that pattern works.
Okay.
It in the future, we are not going to see some totally different kind of storm than has ever happened before. We will see the kinds of storms that are happening in another place move to a different place. So the importance of quaternary science is to be able to look at the whole global picture and to have an understanding of how nature operates within that picture as a kind of habit, a kind of behavior, instead of thinking it as some mechanical device like a machine that we can say how it will work at a particular time at a later time.
Thank you, sir. Thank you. Yeah.
Thank you, Vikil. And there is another question. Snigdha, Dr. Snigdha, can you unmute yourself?
Yeah. Yes, please. Yeah, good morning. My question is, it was very interesting talk, and so questions are also a little basic, I would say. I had seen one photograph that is from central India, Narmada. So having walked in that terrain and also in the, Ganges basin, basic question is when we find different stack of deposits, which we are saying slack water deposits, it is easier to identify on in a plain where the rivers are not frequently flooding. But when we come down to a dynamic or the terrain, much towards the when the river is meeting the sea, there this kind of, because there are a lot of resedimentation also. So this identification sometimes becomes a little challenging. So I would request your kind, perspective on this, how to go about identifying slack water deposits on the plains.
Well, this is an important question, and it has to do with the variety that we have in fluvial systems. The slackwater deposits that we study are largely characteristic of bedrock river systems, because in those rivers, there's a large change in stage or water level with the discharge. But on a large alluvial system like the Ganges or the lower Ganges, the lower Brahmaputra, you have an alluvial river which has a channel that adjusts to the flood size, but the channel will get smaller if the floods are smaller, and they'll get larger if they're bigger, and it's deformable. So one has to use a very different kind of paleohydrology for those rivers than you'd use for the other kinds of rivers. So part of the issue of having nature inform us is to develop an understanding of exactly what nature is telling us in those particular kinds of rivers. In a sense, you have to think like the river thinks. And I know that sounds a little strange, but it comes from your experience and your scientific study. It's like a detective, you know, the famous detective Sherlock Holmes. He tries to think like the criminal that was doing the crime. Now we're looking at nature. Nature's not a criminal, but we should try to put ourselves in the mind of nature, so to speak, and to think about how that behavior is leaving clues as to what was happening. For that, we need to be able to look at different kinds of natural environments. Hope that helps.
Okay, thank you. And another question, it's like, do we have any kind of thickness versus magnitude of paleo floods that we can establish in some particular terrain also?
Are you asking about magnitude versus frequency of paleo floods? Is that?
Yeah, we find different thicknesses of slackwater deposits, and
Yes.
we also know about catastrophic floods where, say, some big boulder or something that has come onto the surface, and you have it is stored somewhere. One picture was shown like that. Now we also find different stacks of deposit. I mean, different thickness. So based on that, can we also think about the magnitude of the flood?
Yes, well, there's always some possibility to relate to magnitude, and there are varying ways to do this. The study of boulders can be a bit problematic because one has the boulder deposited, but the critical conditions were the conditions under which the boulder was moving and when it was initiated in the motion. And we don't have a direct evidence of that. Always when dealing with a kind of paleo record, you don't just look for one magic indicator like the movement of a boulder. You look for the whole context of how other pieces of evidence fit together with that particular kind of evidence, and you use those as a check on the hypothesis that you're generating from your one form. If you recall, I talked about testing the abductive idea with consistency, coherence, and consilience. And I said I didn't have time to discuss those, but those are the procedures that are utilized by an investigator in the field. Experienced field quaternary geologists use these methods all the time. They don't often put those names on them and talk about the logic they use because they are following the sort of experience they gained from working with a teacher or a mentor. But what I have tried to do is to express what happens in logical terms, and it's much more complicated than, say, when a physicist is doing an experiment. The logic they use is very simple and is easy to express in logical terms. But what a quaternary scientist, like an ecologist or a geologist, uses is a very complicated form of logic, but they utilize it intuitively. They utilize it by the experience they've achieved with their mentors and their colleagues. They don't actually try to analyze what it is they're doing. So I'm kind of strange that I do that. but one of the reasons I do that is that there are sometimes these scientists, the modelers and the physicists, they look down on geologists as people that are kind of a lower class, or engineers, for example. They think that these people out studying sediments and the like are just having a good day in the sun or something, and that's completely wrong, because the logic that is utilized by a field worker and investigator is far more complicated than what they do. And there's a famous statement by the nuclear physicist Lord Rutherford, where he said that there's only two kinds of science. One is physics, and the rest is stamp collecting. And my answer to Rutherford would be, well, if he ever tried to do geology, it would be like stamp collecting, because he's so ignorant of what it is all about.
Thank you.
Thank you very much.
One of the things that worries me is, how do you establish the completeness of a record?
The complete record.
How do you establish a completeness of a record for any situation?
Well, at any one place, the record is often incomplete. Sometimes you are very lucky and you find a very good, let's say, stratigraphic sequence or a very good set of preservation. But as in all geology, you have to put together the understanding in space and time. So we utilize tools, we utilize correlation, we use geochronology, we utilize modeling, but we utilize modeling to interpret nature, not modeling to say what nature is doing. But we use the modeling as an aid to our analysis, and by putting this together, as I said, like a detective, we can get more of nature's message. It's never totally perfect, but whatever we get, we know is true. And that is its advantage. And another thing about extremes, which is maybe in my work, is I find that the most extremes, the things that are the rarest and most least understood by other means, they have left the best records, the ones that are most readily able to be discerned. So it's one has to get into the whole feeling of this particular kind of way that nature is operating to have that sense to resolve the problem you are asking. We can't ask nature to be perfect. We have to take nature for what nature presents to us.
Pradeep, Dr. Pradeep Srivastava has raised his hand. Please, Pradeep.
Professor Dr. Baker,
Yes.
I have been working in Himalayas for past 4 years, and we finished a couple of studies in the two extremes of the Himalaya. One was the Brahmaputra Valley, where the floods are as large as being qualified to be called as mega floods, 10⁷ or so cumex discharge. Whereas the Indus, which lies in the rain shadow zone of Himalaya, of ISM, Indian summer monsoon, the floods are 3 orders of magnitude lower, but they're frequent. The thing is this, you talked about the black swan effect. And both the floods, they qualify, given the climatic and the geomorphic conditions, to be called as black swans, extremes. And
Right.
With my experience working in the most populous part of the mountains, is this the administrators are trained to quick fix the problems. And in the mountains, these floods behave as they bring sediments from the most steepest part, and they deposit the sediments. The flood sediments are deposited in the lower relief zones, and that's where they build the landscape, these floods. And most of the towns are established, are sprawling on these low-lying areas of the mountains. They may be in Ladakh, they may be in Brahmaputra Valley or Siang or Tibetan part of these valleys. The thing is this: we know that the most of the floods are there, and the towns are sprawling on these. But these floods are, say, 1,000 years. A recurrence of they have recurrence of 500 years or 1,000 years. That's beyond the human times. The lifespan or time cycle of humans. And I was unable to build interface between the administrators, the policymakers, and the geologists, just because of the uncertainties, time scales, and the problem is, as you said, they are trained to quick fix the things. They don't want to see something which goes beyond the human time scales. So, what is your take on this?
Well, you're talking about a difference between an engineering viewpoint and a scientific one.
Yes.
The engineer is tasked with solving a problem, and they need to do that within limitations. They are limited by available money, and they are limited by time. And they try to come up with a resolution in that framework.
Right.
But in doing that, they are not discovering anything new. They are utilizing pre-existing information. And the black swan effect that you talked about is where the unexpected happens. What the scientist does is not to tell people what to do. The scientist, in my view, is responsible to let them know exactly what nature has done and to impress upon them that that is a real possibility. Now, how they resolve that should be an engineering question. And it should also be, in a democracy, a political question. People need to decide if they are willing to accept the possibility of total destruction and loss of life in such an immense event, or if there should be some sort of action taken, a warning system, maybe some place of refuge, something in case that extreme kind of event occurs. So I think one of the problems is that the engineers are often dismissal of something that is not within the framework of the textbook they read or the existing facts. And the scientists can't say what the decision is that should be made. But I think if the scientist presents what nature has said as a reality, and then it is the responsibility of the political leaders and the engineer to say, we know this is a reality, but we will ignore it, and then see what the people say about that. I'm being a little extreme in that, but that is. I mean, it's about telling the truth, and it is not scientists who are saying it. It's nature saying it. And I think that, that sounds very simple, but I think it is not expressed enough. I think the scientist, the quaternary scientist, needs to be more powerful in their statement, but not because they are experts. It's because they are speaking for nature. And then, in a democracy at least, there should be a public public idea about it. This has actually happened with nuclear power. The engineers argued that nuclear power stations were very good to have. And then there were some nuclear accidents in the United States, 3 Mile Island, in the former Soviet Union, Chernobyl. And then there was a huge reaction of the public against nuclear power, even though the engineering said the risk was very low and you got all this benefit. The public was completely against it. And that is because they understood the possibility of that black swan type event was just too much for them to find acceptable. So I don't know the outcome of this, but I think that it's something that should be thought of more in terms of the ethical responsibility of scientists for issues like the one you're talking about.
Yeah, I think with the lot of growing population pressure, we also have quite a bit of responsibility, and we need to rejoin hands in terms of Himalaya, Gangetic Plains, Bangladesh, Nepal, and these areas are really under stress because in 2013, nearly 6,000 people died in Himalayas in this flood. 1,000 people died in Ladakh, where the population density is too low. So I was really wondering that, how to sensitize people. Okay, thank you. I think I'll keep on discussing this thing with you in future also. Thank you, sir.
Okay. Keep up the good work. Yeah.
I think there are three more raised hands. Rajiv, Saraswat. Can you make it short, please, because we are running out of time. Then we have Minto Albert and Alpa Shrina. We have a few questions from the YouTube viewers also. We would like to read them also. I hope, Professor Baker, it's okay. Is it okay to take any questions still?
Yes. It's getting a little late here, but let's take the questions you have that you said.
Yeah. Okay, Rajiv, Dr. Rajiv Saraswat.
Yep. Thank you, Vinita. Victor, we geologists, like it or not, the modelers are going to have a big say as far as policy is concerned. How much the lack of extensive records of extreme events contributes to these models underestimating the possibility of such events in future. We in an area, if we don't have extensive records of the past extreme events, that probably contributes a lot towards these modelers not paying heed to the geologist and then underestimating those extreme events.
Yes. Well, the fundamental problem is that basically what is happening with a theoretical model, it is what the theoretician, utilizing principles of physics and the like, is saying about what nature will do. That logic only works if you are able to test the outcome by correspondence to a reality. And what is unfortunately done in regard to floods is it is assumed that an extrapolation from the limited experience that is observed conventionally is what shows you that extreme. But that has a causal problem because the extreme may be caused by something totally different than what the small events are caused. So what I mentioned, the underdetermination of theory by data, in the case of extremes, there is no test of the theoretical model. So there's no way to know anything about its validity. It is like saying something and having no way to check what you're saying. That's why nature is important, because we know that is something that is real in terms of it actually happening. Now, this is not a communication, this is not a conversation that's easy to have with a modeler, because they are thinking in a completely different way about the problem. But it is a very important issue if we want to come to grips with black swan problems and the kind of thing I'm talking about. And I think increasingly, as quaternary scientists, we will be encountering those kinds of problems.
Thank you. Thank you, Professor Baker. Alpa Sridhar, are you there to ask a question?
Yes, please.
Okay.
Good evening, Professor. A small question. Actually, I just wanted to ask how relevant is it to correlate the occurrence of floods with the climate change, maybe present or past in both scenarios? How do we, where do we stand? How can we correlate the flood events with the climate change? Because floods occur in any climatic conditions.
Well, correlation, of course, used to be done by inference in regard to the character of the sediments, but now we have increasing technological helps with magnificent forms of geochronology, which all have to be interpreted relative to the circumstances. But those aid us immensely in being able to provide a picture of the environment associated with any particular phenomenon. Like flooding is going to be associated with environments that are responsive to climate in other ways. And the whole picture of that environment may allow us to understand the causative elements that are associated with that flooding and relate them to the general environment in which the flooding occurs. And then that understanding can then be taken to either its relationship to past conditions or to ways in which the future conditions could possibly change, inferring that, in a sense, nature's habits that one is able to get a lot of information about in the past can be extrapolated to the future, not as single points of data like a flood on a frequency curve, but as a whole interactive, understood way of nature operating going into a future time. And those possibilities can then be utilized as a way for people to be able to interact with that issue, such as what we were talking about in regard to people living on a flood-prone area on a major river.
Right.
Yeah.
Okay, thank you so much.
Thank you. Linto, Dr. Linto Albert.
Yes, I'm here. Thank you, Professor Baker,
Yes.
for a wonderful lecture. Actually, I wanted to ask you a basic question regarding where, for the sampling point of view, where is the best place for sampling to get spatially or temporarily continuous record from your vast experience in working with the value of flood sequences? That's the first question. One more is there that's in line with what our previous participant asked. Can we actually correlate with this paleo flood sequence with a high monsoon intensity? I'm talking about monsoon-dominated area, because a flood normally occurs during extreme weather events. Is it so? I'm just asking your clarification for this. Thank you.
Yeah. Well, obviously, the monsoons operate on annual timescales. So if you want to study floods relative to a short time scale, you need a geochronology that is going to be able to be utilized like that. Something like lacustrine sediments or tree rings or some chronometer that is going to be able to be very, very fine. So what was the other part of the question, though?
What is the best place for looking for the
sampling? That is going to depend on the kind of environment that you're studying, and also what the purpose of your samples are. If you just want to do textural analysis of your samples, of course, you can take that to a laboratory relatively inexpensively. But a lot of what we're interested in is the geochronology. And certain kinds of geochronological tools, whether we're dealing with optical stimulated luminescence or radiocarbon dating, these are expensive. We also have cosmogenic nuclide dating. They can be very expensive. So we have to think very carefully how we can maximize the information relative to the sampling that we do. In a vertical sequence of flood deposits, we would be interested in the data that gives us the relationship that is most important for our study purpose. So, for example, the total length of the record is very important. The date of the largest event that is indicated within the record could be very important. Less important will be the whole sequence of events, because you can just count the numbers relative over a particular time scale. So I'm just giving examples of the kind of thinking one would do in regard to a sampling analysis. Again, it's like the detective at a crime scene. The detective walks into a room where a crime has taken place and they can't measure everything. So they utilize their experience to look for the things that look to be most relevant based on their past experience to understand what was going on. And again, experience comes into play. Describing the logic of it is a little more difficult.
Okay, thank you.
Thank you. We've taken the last question. Tarushika Singh, are you there? Or should I read it from the chat box? You've typed a question. Oh, she's not there. But she wanted to know how to interpret paleoflood stratigraphy. Chances are there with younger deposits lying up to the stratigraphy ought to infer younger events to be more extreme compared to the underlying older SWDs. That was it. I wanted to ask, give her a chance to ask the question herself, because this is not very clear. I think she's not there. Yes.
Yeah, it sounds like the question has to do with if you're developing a vertical stack of sediments that obviously the highest in the sequence is going to be the evidence of the largest event, but you may be burying other events. You can't work that out from one stratigraphic section. You have to look for correlations to other locations where you can trace a particular event to its highest elevation. So you would need to do correlations along a whole section of river and try to work that out. In a paleoflood study that is done for, let's say, an engineering purpose, you will have to do that with resources that are consistent with what the client wants to pay to get as much information as possible. But there are ways to do a fairly streamlined study by focusing on the evidence of the largest flood that is within the particular area, and focus on such things as the number of floods that exceed a certain threshold. There are ways to structure a study to get varying amounts of information. This is, of course, a difference between science and engineering. Engineering is always about limitations, limitation of resources to do the study, limitations of time. The science is about getting to the ultimate truth. There's no limitation. It's endless. The scientist is driven by where they think they find out the important truth of nature, and they go there regardless of the cost. The cost has to come later. If they can justify the study, they do that. So there's and we're talking about the attitude that is critical to a scientist. this would get into a completely different discussion. But in my view, science is defined not as facts. Science is defined by an attitude of a community of investigators who are dedicated to finding out what nature has to say to us. And that requires a whole community, and it requires a group of people that are experienced in that quest. So that's what you guys are doing. So congratulations, and keep up the good work.
Thank you. At the end, Dr. Vishwas Kale, sir, please, it would be nice if you could say a few words.
Hello, Vic.
Yes,
Thank you very much for your very insightful talk. And the topic was very relevant because India is one of the few countries in the world which experience all kind of geomorphic hazards. And floods are one of the major hazards. And most of the Indian rivers are highly flood prone. What you have said, I mean, your talk was very interesting, and whatever you have said, is very, very relevant to our situation. What you have said about nature, I also tell my student in a slightly different way. I tell them that nature maintains a diary. It faithfully records everything that has happened during a particular period. And as earth scientists, we have got this diary, and we are trying to reconstruct the past changes in the environmental and climatic conditions. But the diary is incomplete, and it is written in a language that a common man or even a scientist doesn't understand. So, nor we have found a Rosetta Stone in order to interpret the nature's diary. And nature doesn't lie, as you said. So everything that is recorded in the diary by nature is telling you the truth. Now, you, Vic, found one methodology in order to translate this diary. Using some of the pages of this diary, you have tried to translate or interpret by developing the Paleo flood hydrology technique, which is a combination of different sub-branches of geology, which includes sedimentology, it includes hydrology, it includes geochronology and geochemistry, and so on and so forth. And this has helped us to know about what has happened in the geological past. But the problem is that this information is not being incorporated in order to understand what is going to happen in future also. And what you have said in your talk, that the engineers and the administrators, the politicians, they don't recognize the scientific value of this particular information that is generated by earth scientists. I remember, Vic, you had conducted a workshop in National Institute of Hydrology in Roorkee in the 1990s. You interacted with them for 1 week. I was also present there. And many of the engineers and the hydrologists were also associated with some of the projects that we had. But after that, there is no response. They have not taken it seriously because they consider this as a purely academic exercise, not something that should be incorporated in their studies while predicting. And that is the reason we find that the floods which have occurred in the past, I mean, that is an integral part of the monsoon climate. So floods are going to occur with or without climate change. And therefore, repeatedly it has been proved that floods cannot be controlled. So what we can do is only adaptation. Now, for this, we should know that how these calamities have occurred in the past. What were their magnitudes? What is the frequency? And it is the earth science that tells us. And Big Paper have tried to emphasize this particular aspect. Now, before I hand over to the organizers, Vic, I just want to ask you one simple question, and that even a common man is interested to know that, and even scientists have not been able to, convincingly answer this. That how do we exactly define an extreme event? What is an extreme event? Is it the impact? Is it the magnitude? Is it the recurrence interval? Because everybody is talking about extreme event. Anything that happens is extreme. So how exactly we define an extreme event?
How do we define an extreme event? Is that the question? Yes. There is a way to define anything, and it actually goes to the reality of the consequences of adopting that idea. This is called the pragmatic definition, the pragmatic principle of meaning. So the meaning of any concept, like an extreme event, are the practical consequences that come from using that concept. So an engineer may use it one way, a scientist may use it another way, a politician may use it another way. So what I'm saying is there is no exact meaning to any concept, but there is a real meaning in the consequences of using it in a certain way. And just understanding that is to be able to communicate with one another. They don't understand that. That's why the engineers don't communicate with the scientists, because they are using the word extreme, and they're thinking of something completely different than what the scientist is, than what the politician is, than what the public is. They're using the word, but the word means something different. That's a problem. Yes. But that's why I study philosophy. It helps me with questions like that. Not that it solves them, but it helps me understand them.
So we come to the end of this series. I know it's midnight for you there, Professor Baker. I'm so thankful to you to have delivered this talk, such an interesting talk. We could go on and on with lots of questions and queries, because it's such a important and a very ground topic to talk about, and all are something different parts of the world from these disasters. We'll surely bring you back in the platform very soon with some other interesting views of yours on other topics. As of now, I thank everybody who was linked with us in this virtual platform via Gmeet and YouTube also. And I thank my IT team and my office here at the Hydrology Institute of Sciences, and everybody, thank you. So we call it an end of this meeting, and thank you once again, Professor Baker.
Thank you, Vic. Thank you. Good night.
Okay, good night.
Good night.
Yeah. Good morning, I should say, but it's night for me. Okay, good to see you all again. Yeah, all the best.
Talk. Yeah, thank you.
Okay.
Bye-bye.
Bye-bye. Keep up the good work. Bye.
Thank you, sir. Thank you, Carlos, sir. Thanks to be.
Okay, bye.
Bye.
Thank you, sir.
Yeah, bye.